Welcome to my talk on K-means++, few more steps yield constant approximation. This is joint work with Christoph, Julian, and Vašek. The goal of this talk will be to present the key ideas of an analysis of a practical algorithm that achieves a constant factor approximation to the K-means objective. Consider the task where one is given unlabeled data and wishes to group similar ones together to hopefully detect some patterns. Clustering is often used as a first-cut data analysis tool and is often required when there is a lot of data, but only few or even none of them are labeled. Consider the example of the points below, and we wish to cluster them into three groups. A priori, it's not clear whether the blue clustering or the red clustering is better. To get a notion of what is better, one has to define some kind of objective or metric to compare them. One commonly used objective is the K-means metric. Given centers C1 to Ck, the cost is defined as the sum of all points in P to their closest center under the squared Euclidean distance metric. For example, suppose the centers are the red crosses, then the cost of this blue point P is denoted by the gap between P and C3. Although there are infinitely many points in the Euclidean space, one can show that restricting the set of centers to the input points at P only loses a two factor in the objective. Furthermore, it is known that optimizing the K-means objective is NP-hard in general. There are two ways to view the K-means objective. If one is given the clustering, as shown by these red circular envelopes, then it is easy to see that the optimum centers are the centroids of the points in each cluster. For example, the center of this blue cluster is simply the mean of the 4 points that are assigned to it. On the other hand, if we are given centers C1 to Ck, then assigning points to clusters is easy by picking the center that's closest to it. For example, point P is assigned to cluster 3 because it is closer to C3 than C1 or C2. Therefore, we see that if either the clustering is known or if the centers are given, then optimizing the K-means objective is easy. This leads to the following natural algorithm known as Lloyd's algorithm, where one minimizes the K-means objective by alternating between the cluster assignments and updating the center C. So this animation shows an initial set of centers denoted by the stars and how they are updated across different iterations of Lloyd's algorithm. So cluster assignments are indicated by the different colors, and one can see that it changes as the centers are updated. Lloyd's algorithm has no known performance guarantees and is highly sensitive to the initial K centers. So one way to get theoretical guarantees is to initialize with provably good centers, since running Lloyd's algorithm can only improve the K-means objective. The celebrated result of K-means++ is one such way to initialize, and it gives a log K approximation in the expectation. It works as follows. First, you pick a point at random from the point set P, let's say this red point. Then, subsequent points are d-squared sampled to be a center. So d-squared sampling works by weighting points according to their current cost. For example, this point P currently has cost 90. And the probability of sampling P to be the next center is 90 over the sum of all the point costs. So suppose we sample this red point as our next center, then we have to update the sampling probabilities for all the other points. So now this P has cost 40 instead of 90 because it's the minimum of all the current costs. It's the minimum of all current centers. Okay. So d-squared sampling is a random process. So you might pick a point that is not the current minimum cost point. For example, the red point, the third red point over there. And the process terminates after K points have been sampled. So K-means++ is practically efficient, and each sampling step takes dn time due to the need to update the point probabilities after a new center has been chosen. So over K centers, this takes a total of dnk time. Unfortunately, it is known that log K approximation is the best one can show for K-means++. So if we want constant approximation, we need to do something else. So what is currently known? Lloyd's algorithm has been the workhorse in a practitioner's toolkit, as it is a natural thing to try. And typically, people just run a few initializations and just see what happens. From a theoretical standpoint, the best known approximation factor is 6.357 in the general case, and p-task is known for fixed fixed number of clusters k or fixed dimension d. There is also a local search algorithm that use 9 plus epsilon approximation in polynomial time, but it is not practically efficient. In the intersection of theory and practice, we have the k-means plus plus initialization, which we've described earlier. We also have something called LocalSearch plus plus by Latanzi and Solar, which use a constant approximation with just a bit more overhead running time. There is also a bright criteria approximation result that says that one can get a constant approximation to the optimum cost of k centers if one is allowed to use a constant factor more centers. In this work, we answer an open question posed by the authors of LocalSearch plus plus by improving the analysis of LocalSearch plus plus. We show that the log k factor in the running time can be shaved off. Okay, so far we have discussed the problem of clustering and introduced Lloyd's algorithm and the k-means plus plus initialization. For the rest of the talk, we'll describe the key ideas behind our analysis. So our analysis used the idea of settledness, which is also observed in the bright criteria approximation works. We will also introduce what is the local search algorithm and how local search plus plus improves upon it. Finally, we'll wrap up by pointing out the key insight that we have to improve the analysis of local search plus plus. Okay. The bright criteria algorithm can be viewed as a boils into beans process, where the beans are the k clusters of some fixed optimum clustering. And the algorithm will throw O of k balls into them. By throwing balls, I mean like you pick points from the point set into C. So C is your candidate centers. So consider the diagram from earlier, where the dashed envelopes are the optimum clustering, and the red points are the current centers in C. We say that the optimum cluster Q is settled if the cost of the points in that cluster is currently at most 10 times what op pays for those points. So for example, in this picture, we say that maybe op pays less than 10 times the cost of the points in the blue clusters. So these blue clusters are not settled, they are unsettled. So what one can show is that if the current set of red centers are not a 20 approximation, then d-squared sampling will likely pick a point from some unsettled blue cluster, and adding this new sample point will make the blue clusters settled. So if you do this O of k times, then the k-means cost using these OK points will be at most a constant factor of the optimum cost using k points. So this is called by criteria approximation because we're using more points than what the optimum algorithm is allowed to use. So note that the values 10 and 20 are simply constants that we use to simplify this discussion. And in our refined analysis, we will actually generalize the notion of settledness to something called beta settled, where 10 is replaced by some parameter beta. Okay. So let's switch gears and talk about local search by Konongo et al. So how does it work? First, you start with arbitrary k points as your centers. So this red points below. And you repeat the following process a couple of times. You pick an arbitrary point, say this blue point here. Then if there is a red point in the set of centers C, then you can swap with this blue point to improve the k-means objective. You do it. But in this case, you don't, so we just ignore it. And then let's say we pick another arbitrary point, say let's say this blue point here. And we see that if you swap this red point over here with this blue point, so we remove this red point from the set C and you add this blue point to set C. So now our new candidate centers are these 3 red points. Then the cost will increase. The cost will improve. So we will actually do the swap. And one can show that if you repeat this a polynomial number of times, you get a constant approximation. So that's the idea behind local search. So last year at ICML, Latanzi and Solar showed that if you replace the arbitrary choices by k-means plus plus and d-squared sampling, then you can actually show that k log k number of local search steps is enough. And d-squared sampling is quite fast, so local search step is actually quite efficient in this case. For instance, if you have dnk space, then one local search step can be done in roughly dn log k time. So from now on, when I say local search, I mean the variant where the points are d-squared sample. Okay, so a key step in the analysis is to show that in one local search step, the cost decreases by a multiplicative factor of 1 minus 1 over k. So to see why, consider the case where data points appear around the corners of a high-dimensional simplex, where the vertices are distanced big D apart. So for simplicity, you may assume that the distance between the points are essentially 0 if they are in the same corner. So consider the case where k-means plus plus output the centers, where everything lies in the same corner. So in this case, the red points over here. Then in one local search step, one of these red points will be swapped out with a black point in some other corner. So this yields a 1 minus 1 over k cost improvement. But actually, this scenario that is painted over here is not a likely output of k-means plus plus. And this is something that we will discuss later. But the implication of the lemma is that after O of k steps, the approximation factor will be halved. So using the fact that k-means plus plus is log k approximate in expectation, and you use that as a starting point, then you do this local search steps for a total of k log k steps, you will end up with a constant approximation. So a key part of the analysis to show that the lemma works is to argue that when you do these local search steps and you're swapping out centers, you can find a center to swap with your sample point such that you will have an improvement in your cost, or at least, yeah, you have an improvement in your cost, right? So this is because we are maintaining exactly k centers. We're not in a bi-criteria case where we allow more centers than k, right? So the algorithm will actually find the best existing center to swap with. So you'll look through all the case existing centers and find the one that maximizes the improvement. But for analysis, we need a better handle of how the cost changes. So for analysis purposes, consider the following matching process. So let C star be the set of k optimum centers, which might not be in the point set. They're just what optimum has as the optimum centers. And C is our candidate set of centers, right? And we match each optimum center to the closest center in C to form the following bipartite graph. If there is a one-to-one match in this case, or on the left, then we say that these candidate centers are matched. Otherwise, if nothing matches to it, we say that these candidate centers are lonely, denoted by M and L respectively. Okay. If in the local search step, we sample a point that belongs to a cluster corresponding to the one on the left, then we will actually say, okay, let's try to swap the sample point with this candidate center. Otherwise, if it corresponds to some cluster on the right, then we'll say, we look at this lonely candidates, and we'll consider swapping the best one with our new sample point. And what one can show is that there is good probability that a d-squared sample point at each local search step will improve the cost if you follow, will have an improvement in cost if you follow this proposed swapping of the centers. So if this proposed swapping has an improvement, and the algorithm actually uses the best possible swap out of all k centers, then it can only improve the cost further, right? So that's the key idea behind how you want to bound the cost decrease. And this concludes the key ideas from the analysis of local search plus plus. Our refined analysis stems from the following structural insight of k-means plus plus and the d-squared sampling process. First, we generalize the notion of settledness to something called beta settled. And what we can show is that if the current clustering is alpha approximate, then there's not too many unsettled clusters, and d-squared sampling will pick a point from something that's unsettled and make it settled. So in one step, our cost will actually decrease not by a factor of 1 minus 1 over k, but 1 minus cube root alpha over k. Then after some calculations, you can show that running local search for epsilon k steps will yield O of 1 over epsilon cube approximation. So most of our analysis follow the same ideas as the analysis of local search plus plus, but you need to carry across the notion of alpha and beta throughout. Yeah. Our result also holds in high probability in k instead of only in expectation. So to conclude, we discussed an improved analysis of local search plus plus, which is simply running k-means plus plus followed by local search steps. It has good theoretical guarantees while also having practical benefits. For example, in the original local search plus plus paper, empirical experiments show that if you do some local search steps after k-means plus plus, you can improve the performance by around 15%. Another contribution of our work is the structural analysis of clusters. For example, we go beyond the worst case analysis of k-means plus plus, which tell us that there are instances which cause k-means plus plus to be omega log k approximate. The key insight is that most of the costs actually belong to a handful of badly approximated clusters. So just running a few local search steps will actually fix the situation. So this concludes my talk. Thank you for your time, and I'll be happy to take any questions.
Okay, so the speakers is also here, and if you have any questions, you can speak up or you can type it in the chat. We have a question from the chat. So let me mention this. So what do you have planned for future work? Do you foresee future improvements in k-means in the future?
Okay. Thanks for the question, Kiran. So actually for this line of work, it's more or less done, but I can talk a bit about some of the works that some of my co-authors are still working on. For example, two of them, Vashek and Christoph, they're working on the problem of k-means plus plus with outliers, right? So in that problem, it's a variant where you're allowed to remove some of the data points to treat them as outliers, and then you just optimize over the remaining points. So they have some work regarding to that using some very simple algorithm where it's just threshold based. They just do some kind of computation and just filter out based on some threshold metric. And I think that should be appearing in NeurIPS this year if it gets accepted. So that's one line of work. Another line of work is you can change the optimization objective. So instead of having this d squared with respect to the Euclidean distance, some people look at k median or k methods or something in general. Yeah, so these are just some directions that people look at. Yes. Okay. So there's a question by Supana. Could you elaborate what is considered to be the optimum cluster? I mean, in real life data, it is difficult to find optimum. Yes, that's true. In real life, we do not actually know the optimum cluster. So whenever I say optimum cluster in the talk, all these are just based on analysis. So the algorithm does not actually know what's optimum. The algorithm will just do this k-means plus plus sampling and then run the Lloyd algorithm until it converges. And in practice, what people do is they'll just initialize with a couple of different initializations, and then they just run Lloyd and take the best output, right? When I say optimum, it's purely for analysis, because what we want to do when we analyze k-means plus plus is you want to guarantee that there is good chance or that when you initialize with k-means plus plus, the kind of centers you get is already quite good in some sense. Like there are some approximation guarantees so that even when you run Lloyd, you can only improve the objective function. So you do not actually know the optimum. Yeah. Yes.
I also have a question. So for example, if you change the metric, does the whole paradigm still work? For example, if you are you are now looking at the L1 norm as your metric, does the whole paradigm still work? And if not, where does it fall off?
Okay, so that's a good question, because this is quite a very general. That's a good question because it's quite a general, natural question to ask.
because d-squared sampling and the Euclidean distance is more like in L2, right? So one question people ask is, what if you change the metric? And if you look at the analysis, a lot of analysis in K-means plus heavily relies on triangle inequality. So when you change the metric, sometimes things will just break. Like the analysis does not just translate over. The triangle inequality is one big part that will break. Yeah,
I see. Cool.
Okay, there's another question. Oh, sorry, there are two questions. I will answer them one by one. Okay, so the first question is, can the insights from this work be applied to other clustering algorithms, which also have a similar iterative structure? Have you considered that, or is the analysis too bespoke to translate to other algorithms? Okay, so the high-level idea of this algorithm is you analyze your algorithm with respect to some unknown but fixed optimum clustering, and then you kind of measure some potential function and say that, okay, if my current solution is quite bad, then if I just flip a random coin, potentially biased coin, if I just do a biased random decision and do a swap or something like that, then there is good chance that I will improve my solution if my current solution is bad. So that's the high level idea, and I think this analysis approach can be translated to other clustering algorithms if they have like iterative structure, right? So if you're just doing some greedy iterative algorithm, you can say that if my solution is not k, I don't know, k approximate, then with probability 1 over k or some constant probability, the next step will be good. And if my solution is already good, then I don't really care, right? So that kind of analysis idea should be able to translate to other algorithms. Yeah. Thanks for the question. I hope that answers your question. If not, you can just type again. Okay, the next question is, does it mean any cost function fulfilling triangle inequality will work? I'm not sure, because I'm just saying that in K-means plus plus, the current analysis with K-means plus plus with the L2 metric heavily uses triangle inequality. So depends on what cost function you're looking at, it may or may not just translate over. Yeah. Okay. The next question is, on a similar line to different metric, the analysis I think would also depend on the values of the data. Or so is something like ranking based transform to data more useful? Sorry, I'm not sure what you mean.
Yeah, hi. Sorry, I think it's better to clarify. So, please clarify if I'm getting something wrong. In when we're working on the real data, we sometimes see like the transformations or the values are of course going to affect the metric, that is the values of the metric, and effectively also end up affecting the clustering results and the subsequent analysis, right? So I was thinking if like the data values, in the sense of if their transformations or something is kind of more essential for the analysis, or it does not matter from the analysis perspective. So so did you get, or should I give an example?
Yeah. So I got I think I understood your problem. So maybe I can try to ask it again and see whether I got it right. So what you mean is the algorithm and analysis sensitive to data transformation? Like, let's say you just rotate the data, or if you scale everything up by just multiplying every coordinate by 10, or if you shear the data or something like that, right?
Yeah.
Okay. It is sensitive to some transformations because underlying the objective function, we are measuring the squared L2 distance, squared Euclidean distance, right? That's the objective function of K-means. Right. So certain operations is fine, like rotations will not affect the output, but or the objective value. But if you do something like sharing the data or things like this, then you will definitely change the output of the clustering.
Right. So the further analysis is also going to be affected by that, right? So I just wanted to.
So what people do when they analyze K-means plus plus is they just assume that the data given to them is already transformed to whatever form they want, and they only care about clustering on that data given.
Okay.
Yeah. They don't do any transformations after that. Yes.
Okay. Sure. Thank you.
Yeah. No problem.